Hey guys, welcome back to chapter 14. What we're going to talk about now is just some limitations of buffers. So there's a point at which they will do their job. There's also a point where they won't do their job anymore. They're kind of outside of the range of being successful. So that's what we're going to talk about in this video. It's just a very qualitative approach to what is a buffer's capacity, like what is its range. So buffer effectiveness depends on two factors. First, it's going to depend on the relative amounts of acid and base and the concentrations of the acid and base. So when I talk about a buffer's effectiveness, what I mean is, like, how can we make the most effective or the best buffer? How much of the acid and base should we add? What should the concentrations of those acid and base be? So that's one of the things we're going to talk about. The other thing we're going to talk about is buffer capacity. So what is the maximum amount of acid or base that a buffer can neutralize? And then lastly, we're going to talk about a buffer range. So what's the best range for a buffer to maintain that pH and to on acids or bases? The first thing we're going to talk about is the buffer capacity, so making the most effective buffer. The most effective buffer is when the concentrations of the weak acid and base are relatively high. Okay? What I'm about to depict is like a series of tables. So these tables are just an illustration of statements I'm making, just proving to you that it's true. You're not going to be tested on these tables. You're not going to be asked to recreate these from the standpoint of a buffering capacity. But I wanted to show you guys what I mean by more effective at a higher concentration. So here in this buffer, we have 0.5 molar of our weak acid, 0.5 molar of our conjugate base. And the initial pH of our buffer is 5. We're going to add 0.1 molar of a strong base. And what we see is that the final pH, or the pH changes by just 0.02, right? So it stays pretty much the same. Now if I go through the same process, but the concentration of the acid and base are much lower, so it's 0.05 weak acid, 0.05 weak base, I add the exact same amount of my strong base, what we'll see is the pH changes significantly. So to summarize, it's more effective if the concentrations of the buffer are higher than if the concentrations of the buffer are lower. The next thing we're going to talk about is that kind of ratio between the acid and base. So they're most effective when the concentration of the acid and the concentration of the base are equal or close to equal. Okay. So in this example, we've got equal amounts, so 0.1 molar of our weak acid, 0.1 molar of our conjugate base. Initial pH of our buffer is 5. If we were to add 0.01 of a strong base to this, we see that the final pH is 5.09. That's roughly a change of about 1.8%, so about a 1.8% change. Here I see the concentrations of my weak acid and conjugate base are vastly different. So the concentration of my acid is 0.18. The concentration of my base is 0.02. So very, very different concentrations there. The relative change is a little bit harder to see because the initial pH of this one is much different than the other one. But the initial pH is 4.05 and the final pH is 4.25. But the big take home here is the change in pH. If I were to make that into a percentage, it's about a 4.9% change, where this one was only a 1.8% change. So what that tells us is that having the concentration of the acid and the base be relatively equal, that's a better scenario for us. Now we're going to talk about a buffer's range. So a buffer is effective when the concentration of the acid and the base is roughly 0.1 below and 10 above. If I were to plug this statement, because it doesn't really mean much to us, like what does that even mean? Well, if I were to plug that statement into the Henderson-Hasselbalch equation, what we'll find is that a buffer is effective within plus or minus 1 of the pKa. So if the pKa is, 3.5, it will buffer anything that has a pH of 4 down to 2.5. So it's effective between plus or minus 1 of the pKa. Okay. The closer we can get to the pKa, the better. So if let's say we have a buffer that has a pKa of 3.5, if we can find a solution that has a pH of 3.4, that would be the best scenario. So we want the pKa to be as close to the pH as possible. So in summary, concentration of the buffer components are high, that's good. Concentration of the buffer components are equal, that's good. And then buffers will be effective within plus or minus 1 of the pKa. So here's an example just to kind of drive home that third point. So which of the following acids would be the best choice to combine with a sodium salt to make a buffer with a pH of 4.25? So whatever it is that we're trying to buffer has a pH of 4.25. Which one of these would be the best buffer to use? So we want to find the pKa that's closest to 4.25. This 1.95 is outside of the range, so it's greater than plus or minus 1. This 3.34 is also outside the range, so it's greater than plus or minus 1. And this 7.54 is also outside the range, so it's greater than plus 1 of the pKa. So the only buffer that we can possibly use is this formic acid buffer, because we want the pKa and the pH to be this as close to the same as possible. So that's just a really quick qualitative look at what makes the best buffers, and then in what capacity and what effectiveness will they work. I hope you guys found this helpful.